Okay, so we are going to talk about something called entropy. So we're talking about thermodynamics, and let's just review what we already know. So we already know that delta H is something called enthalpy. And remember, anytime you see a variable that is a capital letter, it means it's a state function, meaning it's not very easy, or we're not able to measure the absolute amount, which is why we measure the change in it. So we're measuring the difference in enthalpy. We're going to be measuring the difference in entropy, and then another variable that we'll talk about in thermodynamics called free energy. So before we get too much into entropy, let's just remember what we already know about enthalpy. So remember, enthalpy, this is the heat, or Q, of a chemical reaction, and it's usually in units of kilojoules per mole. Remember that if enthalpy is a positive value, then this is an endothermic reaction, and if delta H is a negative value, then this is an exothermic reaction. So we're switching gears here, talking about entropy. So chapter 9 and chapter 12 really could be one big chapter. We're talking about thermodynamics in both chapters, and you're going to see a lot of similarities in these two chapters. So chapter 9 talks all about enthalpy and heats of chemical reactions. Chapter 12 is now going to introduce something called entropy, which is not a measure of energy itself. Entropy is a measure of energy dispersal. And dispersal, another word for dispersal would just be how spread out is it. So the second law of thermodynamics says that the total entropy of a system and its surroundings is always increasing for a spontaneous process. So the total entropy is always increasing for a spontaneous process. So again, entropy is not a measure of energy, it's a measure of energy dispersal. How spread out is that energy? So a good way for us to look at this is to see, let's kind of see what is happening with entropy in a specific type of process. So let's say we have a reaction and we are going from solid water to liquid water. So you think about what's happening in these molecules of water. So if you have solid water, ice, these molecules are not immobile, they're not still, they're moving a little bit unless you're at absolute zero where all molecular motion stops, but there is some molecular motion even when you're at a solid. When you're at a liquid, there is much more molecular motion. The temperature has increased, so this would be a positive entropy change. Entropy would be increasing as we go from a solid to a liquid. If I say we have liquid water and we're freezing it to solid water, we're going from molecules that are moving more to molecules that are moving less. This would be a negative entropy change. So entropy is a measure of energy dispersal. How dispersed is the energy? So there's three different ways that we can relate. Here's one of them where we're changing phase from a solid to a liquid. But these are the three situations in which entropy usually changes. Three situations in which entropy increases. So one situation where entropy increases would be what we just said, a process in which a solid changes to a liquid or a gas, or a liquid changes to a gas. A solid changes to a liquid or a gas, or a liquid changes to a gas. Because in either of these situations, entropy is increasing because energy dispersal is increasing. So the energy of these molecules as a solid is increasing as a liquid and a gas, or as a liquid, it would be increasing as a gas. So these are a few situations where entropy increases. Another situation where entropy increases is in a reaction which there is an increase in the number of moles of gas. So if you have a chemical reaction that has 2 moles of gas on the reactant side and then 3 moles of gas on the product side, that would be an increase in entropy, because the more moles of gas you have, the more dispersed that energy is. So that's another situation. The third situation is a reaction in which a molecule is broken into 2 or more smaller molecules. Okay, so let's look at some examples. Let's see here. Here is an example of the first situation. So solid water going to liquid water would be an example of this first situation. Whoops. So that's an example of the first situation. The second situation, a reaction in which there is an increase in the number of moles of gas. So let's just find an example here. So let's say here is a chemical reaction. This is for number 2. Here is a chemical reaction. So this is an example where on this side the reactants have 0 moles of gas, and this side on the products has 1 mole of gas. So this overall as a reaction, delta S, is going to be a positive number. Remember, just like in enthalpy, where the sign of the amount was important because it showed you which way the heat was flowing. Was it endothermic or exothermic? Was the heat being absorbed or evolved? The same is true over here. We're going to do calculations for entropy, and then you're going to need to assign a sign to it to say, is the energy being dispersed or concentrated, essentially? Which way is the energy flowing? The third situation is a reaction in which a molecule is broken into two or more smaller molecules. So let's see. Let's just look at cellular respiration, just because that's what we're doing in biochemistry right now. So cellular respiration is the process by which we use the chemical energy stored in the bonds of our food and we make chemical energy. So the formula for cellular respiration, which you guys don't need to know, but it's glucose, C6H12O6, plus 6 moles of oxygen. This is solid. This is gas. Produces 6 moles of carbon dioxide gas plus 6 moles of liquid water plus ATP, which is energy. So this wouldn't necessarily be included in the reaction. But this would have an overall entropy change that would be positive. The number of moles of gas is not changing, but we're breaking up 1 molecule of glucose and 6 molecules of oxygen. So there's a total of 7 molecules over here as a reactant. 7 total molecules. And we're producing 12 total molecules, 6 molecules of carbon dioxide, 6 molecules of water, 12 total molecules. So overall we've increased the disorder. So if you imagine that these molecules are just balls in a container. Here we have 7 balls bouncing around. Here, now we have 12 balls. So you can imagine that entropy is increased the more molecules that you have. So there will be some examples in your SmartWorks homework, in the PowerPoint lecture, in your textbook that will walk you through some different situations, and it will ask you to predict the sign of the entropy change. Will entropy be increasing? Entropy increases as disorder or dispersal increases. Entropy decreases as disorder or dispersal decreases. So we'll talk about how to calculate the actual value later, but for now you just need to be comfortable with assigning a sign, positive or negative, to some of these different processes.